Hello, everyone, and welcome to today's exciting webinar. I am Tim Stark and the host of today's exciting event. I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign and technical director of the Fabricated Geomembrane Institute. This is our sixth webinar of 2020, and the remaining 11 webinars for 2020 have already been scheduled with great speakers and timely topics. And I'll show you the next webinar after Jeremy's presentation. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speaker will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar. Today's webinar speaker is Dr. Jeremy Morris. Jeremy is a principal engineer with Geosyntec Consultants in Columbia, Maryland. Jeremy received his Ph.D. from Wits University in Johannesburg, South Africa in 2001 and started working for Geosyntec shortly thereafter that. Prior to his Ph.D., Jeremy received his bachelor's and master's degree from Imperial College in the early 1990s when Professor Skempton was still working in his office in the Skempton building at Imperial College. So I'm sure that was quite a treat. Jeremy has served as the lead investigator on several US EPA research studies and written guidance on long-term performance and care of waste containment facilities. The title of Jeremy's webinar today is Post-Closure Care of Landfills, which is a topic that has been requested by a number of our viewers over the last year or so. Jeremy, thanks so much for squeezing this webinar into your busy schedule and joining us from Columbia, Maryland. The webinar controls are yours, Jeremy.
Thank you, Tim, and thank you for the opportunity afforded me by FGI to present today. As you mentioned, the topic of my talk today is post-closure care of landfills, which has really been the career focus for myself while I've been at Geosyntec over the last 20 years almost, and indeed was really the focus of the doctoral research that I did at Wits University in Johannesburg. So endeavors in this field go back, over 3 decades or so. So I have quite a lot of material to get through. I'm going to try and get straight into it. I'm going to talk about post-closure care, focusing on municipal solid waste landfills, so subtitle D landfills in the US regulatory context. Overview some of the goals and terminology, and then specifically talk about functional stability and custodial care as ways to define the end of post-closure care. And I like this word end because it has 2 meanings. End means termination, of course, but it also means purpose. To what end are you doing something? So to give purpose and termination to post-closure care, we need to think about things in a performance-based way. And these terms, functional stability and custodial care, are how we go about doing that. I'll do a brief regulatory update, again, focusing on the United States, which is where my practice is. I'll then run through some of the evaluations of post-closure care that can be done to look at where a site is and how it could end post-closure care with regard to its main components, which is leachate management, gas management, and associated water quality monitoring, both groundwater and surface water, cover maintenance, and then miscellaneous other activities. I'm going to try and illustrate that process using case studies that I've worked on over the last 10 or 15 years. We'll finish the webinar with a brief mention of beneficial reuse of landfills. That's really a topic in its own right that could have its own webinar. Some people are doing really creative things, but I'll make a brief mention of that and then wrap things up. So first of all, why end post-closure care? Well, from the perspective of society at large, obviously it gives us the opportunity to optimize resources. We're not permanently marginalizing land as landfills and then close landfills, and it's never available for any other purpose. which was not the intent of the RECRA regulations. So what we're talking about is a site that is used as a landfill. It's then cared for under a regulated post-closure care program for an appropriate amount of time, and then it can transition to some other beneficial reuse which adds value to the community, either recreationally or as wildlife habitat or for commercial or select agricultural purposes. From the perspective of a regulator, obviously you want to end post-closure care in order to provide some cost certainty and liability management in terms of your closed landfill portfolios. And also it's a goodwill and outreach opportunity to be working with a community to look for what happens to a landfill once care is ended, and you can have some beneficial reuse going on. And then finally, even from a regulatory perspective, there's a lot of benefit to ending post-closure care. You can avoid an ever-increasing workload. Obviously, any landfill that closes becomes a closed landfill, and closed landfills have post-closure care associated with them. So what we've seen in recent decades is a lot of sites get closed, sometimes due to consolidation in the waste industry, which is what happened in the USA over the last few decades. But it can also be through regulatory changes such as disposal bans on organics, which can cause consolidation and closure of a lot of sites. But whatever the driver, the thing that you know is when a site closes, it becomes part of the portfolio of closed sites that a regulator needs to keep an eye on. So if we can get some of those sites out of post-closure care, we can avoid an ever-increasing workload, and we can focus regulation and attention where it's most needed. So what are the components of post-closure care that we're interested in? Oops. There are 6 main components, and each of these are going to be very different at different sites, or may not exist at all at different sites. But when you're looking at ending post-closure control systems at a landfill, you're looking at making sure that all of these systems that are in place or were in place can be safely terminated or transitioned to some passive level of management. So from leachate management, you may have recirculation still going on. That would need to be completed before you end post-closure care. You've got leachate collection and a liner system which provides containment. And then you'll have some form of leachate treatment and discharge, either on-site or off-site, depending on what your scenario is. Associated with leachate management, you'll have groundwater monitoring with a network of wells around the site in order to ensure that the landfill is not impacting the surrounding environment. You'll have landfill gas collection with a network of gas wells, generally connected to a flare or a waste to energy utilization facility of some kind. You'll have gas migration monitoring associated with that, generally with a network of probes around the perimeter of a site that allow you to ensure that you're not getting gas migration beyond your realm of control. To maintain these systems, you'll have a level of cap maintenance and monitoring required, primarily, focused on the final cover system, often with some surface water management components tied into that, which may or may not have some monitoring requirements associated with them. And then there are general property maintenance activities such as maintaining access control and etc. So when you're looking at ending post-closure care, you're really needing to examine each of these components and figuring out how you can safely reduce them or completely terminate them. So we have a lot of operational experience about the long-term performance of landfills. So this little cartoon figure here illustrates the passage of a landfill through its initial construction and operating phases on the left, through intermediate cover installation, and then final closure as we move over to the right-hand side. And we have very good performance data over several decades on how landfills perform in terms of leachate generation and landfill gas generation. That's associated with this life cycle passage of the landfill through time. The liner system indicated here, we have a lot of data indicating that as long as a liner remains isolated from air and other factors that could cause degradation, that it should remain competent for decades or even centuries. certainly for the period of time that we are interested in terms of post-closure care. The final cover system, similarly, which includes several layers generally, and importantly includes the vegetation that's installed on the top as an erosion control measure. That provides isolation of the waste, and there's a lot of evidence to show that that can remain competent for a very long term, as long as it is cared for, so no exposure of the barrier materials. So we also have a lot of scientific experience regarding the long-term performance of landfills. Most people are pretty familiar with the 5 phases of landfill degradation as proposed by Fred Poland and others in the 1980s. Other researchers, Peter Kelson and Mort Barles, for example, have proposed that beyond the stable methanogenic or methane oxidation stage 5, there are a series of other stages that could occur if no care is provided for a site and it is allowed to gradually degrade until it eventually becomes an inert mass. But really, I think this illustrates very well what the goal of functional stability is and why we want to achieve functional stability rather than an inert mass, which is how we would probably define organic stability. We have a lot of data regarding the performance of landfills in early stages, and as we move through the phases, things become increasingly more speculative. So what we're seeking to do when looking at functional stability is get to stage 5. That's where everything is stable or exhibiting downward trends, and we want to prevent the site from moving into phase 6, where things become much more uncontrollable and unpredictable. You'd have some air intrusion, some redox changes, some remobilization of metals potentially. So we really don't want to get to organic stability. We want to get to functional stability and then find a way through passive measures to keep the landfill at that stage. Looking at the US regulatory context for post-closure care from a federal level, for MSW landfills, we're looking at RCRA Subtitle D. There's a general assumption that Subtitle D's post-closure care term is 30 years, but actually the regulation is performance-based and requires an owner-operator to continue caring and managing leachate and gas and other aspects of the site until you can demonstrate that there's no threat to human health and the environment. The regulation defines the point of exposure typically as the closest property boundary at which a receptor could be exposed. So, you know, we have a nice definition under a performance-based approach of what the point of exposure is that we're trying to prevent impacts at. And then we monitor at some point between the landfill and the point of exposure, which is the point of compliance. So all of our monitoring wells, our groundwater wells, our gas probes, etc., comprise the point of compliance. That may be at the same place as the point of exposure, but it certainly can't be further out than the point of exposure. Active gas management is terminated when its gas control system is no longer required to control subsurface migration. That's the rule under Subtitle D. There are, of course, other regulations in the US that govern landfill gas control from an emissions perspective. That's the NSPS regulations. EPA has issued some guidance for post-closure care, but mostly focused on Subtitle D. There isn't really any guidance specifically focused on Subtitle D. EPA put out a short memo at the end of 2016 outlining the process that regulators should go through when examining a petition or a request to end care at a Subtitle C site. That's quite a short document, but it packs in a lot of information. There are 2 very large, long, and detailed reports detailing the long-term performance of containment systems at RCRA facilities, and the references for those documents are available here. So what's the goal of performance-based evaluation? We know from looking at the regulation that this is the intent of RCRA Subtitle D and Subtitle C. So we want to end post-closure care in a safe and defensible manner. We want to get to functional stability, that's phase 5 of the waste degradation curve, and not go all the way to organic stability. So how do we define that? We have a definition that was proposed by Swaner's Bioreactor Committee back in 2004, which is shown on the screen here. I reword that slightly in the work that I do to say a landfill is functionally stable when it doesn't pose a threat at the point of exposure in the absence of active control systems. So once your landfill control systems are fully passive or they've been entirely eliminated, then your landfill is functionally stable. And once you're functionally stable, you can end post-closure care. The technical basis for that then obviously is defined in terms of achieving a non-impacting relationship between the landfill and the receiving environment at the POC as measured at the at the POE as measured at the POC. It's performance-based and site-specific. There's no time frame, there's no general time frame associated with care. It's going to depend on conditions at each site, the waste in place, how large it is, the underlying hydrogeology, the climate, and a number of other factors. So there's no specified time frame, but a 30-year benchmark is a good target. So if you're an owner-operator of a landfill and thinking about ending post-closure care in a reasonable time frame, then planning for it over a 30-year period is definitely a good initial target. Some sites may be able to complete care in a shorter time, and a few sites may require a slightly longer time depending on site-specific conditions. As we've noted, we're not concerned with organic stabilization, but we're concerned with a non-impacting relationship with the environment, which means we're really looking at emissions and how they could impact the environment under worst-case release scenarios. To do anything performance-based, we need a lot of data. You can't do any evaluations of performance without data, and you need data to be able to be evaluated in a statistically robust way, which means you need a long data series. So start early, collect more data than you think you're going to need, start collecting it sooner than you think you're going to need it. Because when you get 10, 15, 20 years into post-closure and you're starting to look at doing some evaluations, you're really going to need a lot of data. And then based on our evaluations, we can look at making step-down reductions in post-closure care. So we start with everything fully active. We want to look over time at transitioning activities to more and more passive means, perhaps managing leachate with an on-site wetlands treatment system, and eventually getting to the stage where we can confidently demonstrate that all care at the site can be fully passive. And very importantly, every time we make a change to a post-closure care system, we can monitor the outcome to confirm that what we evaluated and what we predicted the behavior would be is what it is. Once we achieve functional stability and we end post-closure care, something has to come after that. We define that as custodial care, which is a de minimis level of care that would be needed just to take care of the property, kind of similar to property management responsibilities that any landowner would have. And those are going to vary depending on what the previous use of the site was. Custodial care will always consist of some cover maintenance because you'll need to isolate the barriers, the barrier layers in the cover, and you'll need to make sure that the waste is contained. There'll be maintenance of some other site features and generally access controls, unless your post-closure care plan allows free public access to a site, which is possible, but it makes the evaluation of control of impacts at the point of exposure pretty difficult when your point of exposure might be the cover of the landfill itself. You can mandate custodial care through land use controls, environmental covenants, etc. So it can exist outside of the solid waste regulatory program. And very importantly, the owner retains responsibility for a site when it's in custodial care. There's no walk away from responsibilities for a former landfill site, but allowing transition out of post-closure care into custodial care allows much more creative, beneficial reuse options to be considered. Some guidance that's available to do a performance-based evaluation of post-closure care. I'm going to be talking primarily about a methodology that was developed for EREF about 15 years ago. That's the evaluation of post-closure care, or the EPCC methodology. ITRC, SWANA, and NWRA all have guidance documents in one form or another that provide some information on how to go about a post-closure performance-based evaluation. And then if we look at where states are, there's a number of states that have implemented regulations that have implemented regulations or guidance focused on providing information on how to make a demonstration of functional stability, or a performance-based evaluation of ending post-closure care. Two very notable ones here highlighted in green. In Washington State, there's a regulation which requires landfill owners to predict when their site will achieve conditions of functional stability, and then their post-closure care plan and their financial assurance gets linked to that predicted time frame, as opposed to just an arbitrary 20 or 30-year period. And then there's a guidance document issued recently in Florida, 2016, that provides a step-by-step procedure for how to end long-term care at solid waste facilities and transition to a post-regulatory custodial care program. A few other examples here. New York has a recent regulation looking at ending post-closure care and transitioning to custodial care, but DEC defines custodial care within the solid waste program. So a little bit different to how I define it under the EPCC methodology, where it's post solid waste regulations. In New York, it's part of the regulation. So there are always some differences in terminology and thinking, but generally all of these states have issued guidance or regulations on how to do assessments based on performance, rather than trying to meet organic stability goals or just simple stipulated timeframes. So experience that we've gained with the EPCC methodology in the last 10 or so years. The states shown in blue here are where I've done some research type level analyses or internal evaluations of one or more aspects of post-closure care for a landfill owner, but nothing has been submitted. The states shown in orange, which there's 5 of, are where we've done an evaluation and prepared a report that has been submitted to a regulator. And then the state shown in green, Texas, is the site where a regulator has approved termination of a post-closure care permit as a result of a demonstration made. So we've picked up a lot of experience, and I'm going to use this as I walk through the process of evaluating functional stability with regard to the main components of care at a landfill, starting with landfill gas. So how do we get away from active gas management with a lot of monitoring, maintenance, etc., to a passive management strategy? So to start off, we'll need to define and then meet a functional stability target. Where are we trying to get to, and then how do we demonstrate that we've got there? Part of that will include showing a statistical downtrend in collectible methane. We'll need to show then that when we eliminate active gas controls and move to passive gas controls, that doesn't result in impacts. So we'll need a level of monitoring that's focused on showing that transition that you made was appropriate. You'll always have some level of cap maintenance associated with gas control. And you need to make sure, if you've got plans for beneficial reuse of your property, say as a recreational field, you need to make sure that your long-term gas management plan is compatible with that. Once you've confirmed that your system, your passive system or your no gas system is working, you can then be considered to be in conditions for functional stability or custodial care with regard to gas management. And the way I always try to think about where you're trying to get to is, if you could wrap your management system into a general property maintenance program, something that was undertaken by a landscaping company as opposed to a professional engineer or an environmental scientist, then you're really meeting the conditions of functional stability. Some examples in the pictures below of passive controls that can be installed as alternatives to active controls at landfills. So establishing targets for functional stability, there are 3 real ways that we can do this. Either a regulator provides a standard that we have to meet, which is the easiest way in terms of the amount of work you have to do. There are no examples in the US of that. In Europe, I know that Austria and France have proposed some standards for when gas generation levels get so low that managing gas actively using a flare or something like that ceases to be optimal, and passive control measures are preferred. We can define a de minimis residual gas generation rate for ourselves in the absence of a standard. Generally, we look at 10% of the peak as being the de minimis residual gas generation rate. It's a little bit arbitrary, but if you think about what that means 90% of gas production is in the past. So all we're dealing with is the 10% residual gas generation that's left. That'll be in the tail of the gas curve, which might be quite long, but we're never going to be looking at very high levels of gas production relative to where they were in the past. And then a backed specification, best available control technology. Again, some jurisdictions have guidance on that, where passive controls become optimal to active controls. There's a very good example in Ireland of that. But generally, if those are lacking, we tend to go with the demonstrating de minimis residual gas production. So if you have if you have gas collection data through the post-closure life of a landfill, then you can look at what your collection rate was at closure, and you can say, okay, I just need to get to 10% of that. Most sites don't have that. A lot of them have a cluster of data available in recent years, but not so much going back into the 90s or the 80s if they were closed a long time ago. So what we can do then is just do a projection back using an exponential decay function to estimate what the peak flow would have been at closure, and then say, okay, our goal for functional stability would be to get to about 10% of that. And this graph here shows an example of where we did that at a site in Louisiana. We can sometimes combine a backed type specification with this de minimis residual gas concept to develop a a target for functional stability. So this is a site in Washington that had an alternative cover, an evapotranspirative cover permitted. As part of the performance-based design process for that cover, soil oxidation measurements were taken by Tariq Abichu and his team at Florida State. So we then have a graph that says for different bottom fluxes, which we can relate to overall gas production, we know how much oxidation we would expect to achieve. So if we set our functional stability target at 90% oxidation on an average annual basis, which is kind of the 10% concept, but in reverse, that relates to a bottom flux of 6 grams per square meter per day. And we know the overall gas production at the site, so that translates into 120 standard cubic feet per minute. So we've then got our target for functional stability established based on this backed specification. We can look, once we've established our target, we can estimate what the time to functional stability would be. So here's an example of a closed site in Washington where we did that. It was, a very wet site overall. It's Washington. The site consisted of 2 mounds, an older pre-subtitle D unit and a newer subtitle D unit, both connected to the same flare. So we evaluated them together because they were both contributing gas to the same control system. But when we model gas production using LandGem, you'll see with the blue line here that we get 2 distinct peaks, because one is for the older unit and the second one is for the newer unit. We know our peak collection rate, so we know what our 10% target for functional stability is. We can calibrate the model using on-site data. So you can see here the orange data was used to calibrate the blue gas curve, and we get a very close fit. So based on this, we were able to estimate when we did our evaluation that we would expect to achieve functional stability sometime around about 2017 or so. So that then becomes our goal when we're going to make the transition from active to passive management. And then based on that, we're going to design a confirmation monitoring program to show that that transition was appropriate. So we would leave all the active control system components in place until we've demonstrated that we don't need them anymore. A quick example of where we did a transition from active to passive gas management. This is an old unlined site in New York that has a geomembrane cap. So obviously the concern here with stopping active gas extraction is that we might get some pretty significant gas migration monitoring, or we might get unacceptable levels of gas pressure buildup underneath the geomembrane cap. So we designed a monitoring program that would enable us to show that that wasn't occurring. So that involved installing some pressure transducers just below the cap so we could measure pressure buildup in the absence of a vacuum. And then there were some nearby structures, so we put in a passive cutoff trench as a control measure And then we wanted to look at whether we were getting any methane accumulation on the outside of the trench. So is any, in the absence of active gas care control, are we getting any gas migration beyond that passive cutoff trench? We can fix the monitoring duration for that based on the maximum time of travel for migration from the landfill tow to the gas probes. For that, we're looking at time of travel in the unsaturated zone under advection and diffusion, which isn't particularly straightforward, but it can be done. There's some guidance in the EPCC methodology for how to do that. And we calculated that we would need to monitor for 9 months to be sure that if a migration impact was going to occur, that we would have detected it at that monitoring probe there. So looking first at our pressure readings, we set an action level that could result in potential geotechnical instability of the cap, and we never got pressure buildup under the cover anywhere close to that. So we know that the absence of active gas management is not critical in terms of cover stability. And then if we looked at our migration profile, the yellow line here is just an indicator of when we had the flare on. So we turned the flare off at this stage and then started a very rigorous program of monitoring soil gas concentrations at the probe outside of the well. We had a little bit of detections in the immediate phase. I think this was just some residual pockets of methane that were left from the cut-off trench construction. But then for 9 months, we were able to show on a daily basis that we were not getting any methane in that trench. We know that that exceeds the time of travel that we would expect it to take for gas to migrate, and therefore we've demonstrated that our passive gas control system is performing appropriately. Looking at leachate then, so we've been through gas, so leachate, how are we going to move from a system where we pump leachate out of the landfill, we store it, we treat it, we send it off-site, etc., to something that's more passive? Leachate's a little bit more complicated than gas, but we can look at some indicators of functional stability in the same way. There are some gateway indicators, some constituents of leachate that tell us a lot about the overall behavior and trend towards functional stability. I'll talk about that a bit more in a second, but we would want to be able to do a statistical demonstration of downward trend and concentrations below functional stability targets. Again, we're looking at whether a worst case leachate release would cause impacts, again, predicated on some level of cap maintenance. And then we'd want to do some monitoring to confirm that our proposed passive system is performing as designed. And again, focusing on, can we wrap that into some level of general property maintenance as opposed to a regulated program. So long-term landfill behavior, there's a high level of scientific knowledge available for this. Again, remember, with regards to the degradation curves, we're trying to make sure the landfill stays in phase 5, the stable methanogenesis, trending towards methane oxidation and not progressing beyond that. We have a lot of evidence showing that the bottommost layers of waste are well decomposed and act as a filter. So as long as we're removing leachate from the bottom of a landfill, we know that behavioral trends that we've established using that leachate are going to be valid. We see a lot of degradation occurring within the landfill, above that biofilter layer. So, we know that remobilization of constituents of interest, such as metals, is not going to occur over the long term, as long as conditions don't change dramatically. So as long as we don't let the cover degrade and have air intrusion occurring, we can rely on the redox conditions within the landfill staying pretty consistent. Ammonia and chloride tend to accumulate because there aren't mechanisms biological mechanisms to attenuate them within a landfill. So they generally are our main constituents of concern. And then our surrogate gateway indicators of trends towards functional stability are biological oxygen demand and the BOD to COD ratio. So we have some functional stability indicators for what constitutes well-degraded waste with regard to those. And then going through the leachate assessment, we want to confidently characterize our source. So we need to know what's regulated in groundwater and surface water so that we can show that for every regulated constituent, we wouldn't cause impacts at the point of exposure. We need a strategy for long-term leachate management so that we can scale back operation of the LCS. We need to consider the bathtub effect, that is, hydraulic equilibrium. So if you're going to stop managing leachate you need to make sure that leachate isn't going to accumulate such that it would potentially seep out of the side. So, you may need to think about a mechanism for continuing to manage leachate from a physical perspective, even when it's no longer a biochemical concern. And then look at what our passive leachate management options are for that. As I showed in a previous slide, some people have used farmers' windmills to pump leachate, where it's a physical need as opposed to a biological concern. And then, to demonstrate the acceptability of a proposed strategy, we need to define our hydrogeological fate and transport model. Here's some examples of our gateway indicators. So, with regard to BOD and the BOD-COD ratio at this site, by the time we get to where we're doing our assessment, which was sometime in 2012 in this example, we can see that our leachate is exhibiting the appropriate trends and the data are below the functional stability targets that we've established. Comparing to water quality standards, so initially we would do a source comparison, so generate a statistically representative concentration in leachate and just compare that directly to a groundwater or surface water standard. If you can meet all standards using source leachate, if your standards are drinking water standards and you can meet them all, that effectively means you can drink the leachate, so you're not really too worried about managing it from a biochemical perspective. Generally, you won't meet all standards at the source, in which case you're looking at, well, what would the concentration be if that constituent leaked from my landfill and got to a POC monitoring location, either a surface water outfall or a groundwater monitoring well. And we can calculate a conservative dilution factor associated with that based on a simple Darcy flow model with inputs either available from site studies or calculated using models such as HELP. Generally, you'll find at most sites this data is available. Normally, there's been a pretty good hydrogeological assessment done as part of original siting and permitting studies. So generally, you're not having to go out and measure this. It's just a question of finding it in design documentation. So establishing the hydrogeological model, looking at this cartoon here in terms of what's important, while leachate is being managed, which is the red component here, we're removing leachate from the LCS, we're transferring it to a tank, and then it's being discharged offsite. If you're looking to remove that red pathway, then you're looking at, well, what's the potential for leakage into groundwater, and then what's the potential dilution that's going to occur in my subsurface? So what concentration should I be looking at my POC well to indicate whether I've had an impact or not? And then similarly for surface water, you may potentially get seeps. So if you have an on-site stormwater management system with an outfall with some monitoring requirements there, then you would need to show that if you stop pumping leachate, you're not going to end up with impacts at your outfall. But it's important, obviously, to remember that every site's very different, and you need to look at the site-specific hydrogeological model and the geologic setting and see if you can take advantage of conditions there. So here's an example of a site in upstate New York that we looked at. This was an old sand and gravel quarry built into the side of a slope above a river. So if we take a cross-section, the generalized direction of groundwater flow is down the page here. So if we take a cross-section through that, you can see that we have waste deposits overlying a very tight till, and underneath that are shale deposits, which represent the uppermost hydrogeologic, the uppermost aquifer. All leachate drains to a toe drain here, so we have good gravity drainage going on. If we look at what our potential leakage to groundwater as a point of exposure, we can see that our time of travel to the groundwater table is very long. So that's not really a realistic leakage pathway for leachate. If leachate's leaking from that toe drain, it's going to leak into the superficial deposits and head towards the river. So we can look, therefore, at what the potential pathways are to the river. One is indirect leakage through the subsurface, so via that alluvial brown till deposit that's there. Or else we could have some direct leakage across the surface into on-site ponds and therefore to outfalls. We also, at this site, have an on-site wetland treatment system. So leachate gravity flows to that system, gets treated, and then there's an outfall from the wetland treatment system to the river. So that's another potential pathway for leachate to leak to the point of exposure, which is the river. So finally then, looking at our last component of functional stability and maintaining final cover conditions. So what are our indicators of functional stability for a landfill cap? There are regulatory requirements for the cap, which is primarily that it maintains its role as providing containment and isolation of the waste. There are performance requirements for the cap. It needs to be shown to be geomechanically stable, need to show that significant settlement is completed. And again, in keeping with our overall approach of saying, well, let's look at when we reach a point where future changes are going to be de minimis, what we do is establish a 5% change on an annual basis as the target for functional stability. And I'll look at some examples of that. We've also got to remember that there are performance requirements for the cap that the outcome of previous evaluations of leachate and landfill gas management are probably predicated on. Gas and leachate are always going to assume that there's some control of infiltration of rainwater or emission of landfill gas. So if you've done an evaluation in previous, looking previously at leachate or landfill gas that assumes there's a certain level of cap in place, then you need to ensure that that level of cap performance stays in place. So again, what management is required to maintain containment, maintain the integrity of the cover. The pictures at the bottom are all different examples of landfill caps. Over on the left-hand side, we have a typical subtitle D cover system, soil layers overlying a geomembrane and clay barrier system, kept neatly mowed so that trees aren't potentially growing into the cover and damaging the geomembrane, a nice stormwater management with a perimeter drainage swale. So what we're looking at is maintaining that functionality with as little effort as possible. In the center, we have a couple of pictures of alternative covers using evapotranspirative tree systems, either a pretty structured one on center left or a more natural type distribution of trees on the center right. And then, increasingly people are looking at exposed geomembranes or exposed geomembranes with an engineered cover, such as closure turf as alternative cover systems. Again, what you need to show as part of your evaluation is that you can maintain the integrity of the barrier layer. So whatever your cover system is, and for an ET cover, your barrier is basically your sponge and pump mechanism. But whatever it is, you need to show that you can provide the level of care that's necessary to maintain that. And then again, we're always asking, can a landscaper perform this task, or does it need to be done by a professional? Because if a landscaper can do it, then you're definitely in a post-closure, in a post-regulatory custodial care kind of phase. So estimating the time to functional stability with regards to cap settlement, we model this based on secondary settlement. By the time you're doing this kind of evaluation, you're a couple of decades into post-closure. All primary settlement, consolidation, even mechanical creep should be completed. So what we're really looking at secondary settlement, which is related to landfill gas generation, waste degradation. So once the rate of waste degradation starts to slow, the rate of secondary settlement will start to slow, and we can show that we should have achieved a condition where the annual rate of change is going to be less than 5%. So we don't get a lot of differential settlement, because it's differential settlement that creates cover system upsets like depressions and erosion and ponding, etc. So a very simple process for estimating that. Here's an example from a landfill in upstate New York where we modeled this, and we showed that we should have achieved functional stability sometime around about 2003. Once we model it, obviously we then need to confirm it. A couple of ways we can do that. One is if you have settlement plates installed in the cover, then that gives you a very nice way of directly measuring settlement. Not many sites do that, but this is an example from a small municipal landfill in France that I did an evaluation on. So we showed that the site would have expected to be functionally stable in year 2015, and we were in year 7 when we did the analysis. So using the settlement plate data, we were able to show that the model meets the data pretty well, and that we would expect that in another 7 or 8 years' time at this site, we would be meeting the functional stability criterion. If you don't have settlement plates, you can use topographic surveys, aerial flyovers. So this is an example from a site in New York where we did that. So we modeled settlement, which is the blue line, and we predicted we would achieve functional stability in 2006. And then we were able to look back through a series of topographic surveys and look at the difference in settlement on a year-by-year basis and fit the red data to the line and show that we really were achieving those conditions that the model had predicted. So finally then, beneficial reuse of landfills is an important component of any evaluation of post-closure care. If you're looking to complete post-closure care, get your landfill to a fully passive condition so that you can petition to surrender your post-closure permanent transition to custodial care. You need to look at mechanisms for putting your closed landfill to work. An important part of this is custodial care is still care, and care costs money. It may only be a few tens of thousands a year, but that's still money that needs to be available on a year-by-year basis. So one way of funding custodial care is through beneficial reuse. If you can lease your site out as a host site for a renewable energy project, or if it can become a community asset with recreational facilities such as ballparks or cycle tracks or so on, if you can find a way for your site to earn the money that it needs to pay for the de minimis level of care that is represented by custodial care, then you've really managed to get to a kind of perpetual funding scenario where the site is paying for itself, and it's kind of rehabilitated back into society in a beneficial way. So this is really what we're always trying to get to. So in summary, under a performance-based approach, post-closure care is continued for as long as necessary, and you have tangible targets to aim for in terms of demonstrating completion of post-closure care. You define those targets in terms of functional stability, as we've looked at through this presentation, and quantified functional stability in terms of leachate and landfill gas emissions and what their potential is to cause impacts at the point of exposure. You really need a lot of data, and you need a lot of end-use planning so that you know what your end-use condition is that you're aiming for, and you have enough data to do the kinds of analyses that are going to be required. In particular, with regard to leachate management, if you're having to demonstrate that your leachate meets all regulated parameters at the site with some statistical confidence, you're going to need a decent amount of data, and it's got to be data collected over a long period so that you can do a longitudinal type data analysis and really have a lot of confidence that you've got downward trends in concentration and you are at or below limit values in each case. There are a lot of tools and guidance that have been developed and available to evaluate functional stability. I've focused on the tool that Geosyntec developed with EREF, the EPCC methodology, but as I mentioned, there are tools available from other groups. And ultimately, what you're looking at doing is always transitioning from fully active control to mostly passive and then fully passive. So with landfill gas, you're looking at going from active flaring to partial flaring with some hotspots at some hotspots, while other parts of the site move to passive flares like tiki torches, for example, and then from there transitioning away from all active and passive flaring towards use of biocovers, biovents, whirligigs, etc., so that you've got a full passive system that a landscaper could care for. And similarly with leachate, you'd be looking to transition away from collecting leachate and trucking it off site or some very active control system towards doing de minimis level of treatment on site, and then eventually showing that you can completely stop your leachate collection system, establish hydraulic equilibrium in terms of infiltration through the cover versus leakage through the liner, and demonstrate that your site is truly functionally stable. You're always going to have some cap inspection and maintenance requirements through custodial care, but once all your controls are passive and really all you're doing is cap inspection and a few other activities, the regulated post-closure care program should end and custodial care would commence, and there are beneficial reuse options that help pay for the residual care that is required under that custodial care program. So with that, I finished speaking. I think I'm 5 minutes or so over, but I think we're now open the floor to some questions that are being received.
Yep. Great, Jeremy. Thank you for a very interesting presentation. We do have a bunch of questions. First one's kind of loaded. What types of geomembranes can be considered for the final cover system?
I mean, generally, when we're designing prescriptive covers, so that's where you have a geomembrane barrier overlying some kind of clay or low permeability soil, and then it's protected with a drainage layer and a layer of topsoil above for vegetative support. We are generally using linear low density polyethylene for that. I think normally a 30 mil thickness, but I mean, that's a design question. When the landfill designer is going through the process, they can really consider any geomembrane at all, as long as the evaluation that they do shows that it's going to have the requisite durability, hydraulic performance, puncture resistance, etc. But as I say, the most common material that Geosyntec specifies for cover systems is LLH, linear low density polyethylene.
Okay. Next is, are there additional considerations for ending PCC, post-closure care, of a landfill which has/is experiencing elevated temperatures?
Yeah, I would say that there definitely is. I mean, the thing with post-closure care is to do an evaluation of ending care and demonstrating that it's appropriate to turn off or scale back your control systems. You have to show that you really have a very good handle on its long-term behavior and that its behavior is predictable and it meets the results of models that you've applied. So I would say for any landfill that's undergoing elevated temperatures, at some point those landfills will be able to close and enter post-closure care and eventually terminate post-closure care. There's going to have to be a lot of work done to make sure that we understand the internal processes that are going on so that we can do the demonstration that says we understand the processes, they're predictable, we've done this demonstration that shows downward trends towards a target that we expect to meet, we've done some monitoring that shows that we met that target, and therefore this site is controllable and can transition out of care. I don't think there are many sites with elevated temperatures that are closed. I think most of them are still have some active operations going on. But it hasn't been an issue that I've looked at yet because there aren't landfills that are 10, 20 years into post-closure that have been experiencing this.
Okay. Do you know of a case or an engineered landfill that has actually completed 25 years of PCC? If so, has there been any investigation at that site to assess the state of the waste? And the idea is, if so, then you could use that to calibrate your, say, 25-year, et cetera, models.
Yeah, there've been a couple of sites, including some that I've worked on, where people have done investigations of in situ waste properties through time. As I noted, that data doesn't really help you when you're looking at post-closure care from a performance perspective and you're defining the end of care in terms of functional stability, because that's really focused on what are the potential emissions from the landfill and what's the potential for those emissions to cause impact. So as long as I know that those emissions are going to be predictable, which I do, as long as I maintain the flow regime within the landfill that I talked about, ensuring that leachate emerges from the bottom and isn't spilling out from the sides, so that you've got the effect of that biofilter taking place and you've got predictable leachate quality associated with it. Within a landfill waste mass, there's always going to be some pockets of waste that are less degraded and some pockets of waste that are more degraded. So if you try to define completion of post-closure care in terms of there being no pockets of undegraded waste or not fully degraded waste within the landfill, I don't think that's going to be achievable until you were able to get all the way to that phase 8 of the landfill behavior model that I showed early in my presentation. And we have no data showing a landfill that's gone all of that way. Expectations are that it would take, upwards of 50 years for a landfill to really achieve that. So I'm not really focused on that because I don't think it's useful for us to try and get there. I think it's more useful for us to get to a point of functional stability and show that we've achieved that and with a de minimis level of care. So, acknowledging that we're always going to have some care associated with maintaining the cover, but that as long as we do that, we're not concerned about there being some undegraded waste in the landfill. I think that's a much better approach in terms of, managing society's resources and land assets.
Yep. Jeremy, I know you have a meeting at the top of the hour, so let me see if I can give you maybe one or two quick ones, and then we'll address the rest of these questions in your podcast next week on May 26th. So those of you that haven't entered questions or still have questions, send them to me and we will get them answered during the podcast on May 26th. Jeremy, for the New York example, where the landfill was near a river, was there any consideration of the impact of flooding or meandering into the landfill?
Yes, some initial studies had been done, much earlier than the evaluation that I was doing, which was 25 plus years into post-closure. But the landfill was, the toe of the landfill was outside of the 100-year floodplain, from what I recall. So we reviewed the documents that had been done previously to look at that, but we didn't specifically consider it as part of our analysis because the landfill was outside of the floodplain.
Okay, maybe
but that would be an important consideration for a very low-lying landfill.
Yeah, absolutely. Maybe this is the last one. Is there a concentration of methane, not volume, and a concentration that would be a good indicator of stability?
It's a good question, and it's something we have looked at. Generally, I think no. Methane concentrations, particularly when they're measured at point sources like wells, can be quite deceptive, and particularly when we're getting towards the tail end of generation. What happens is you get a very small volume of pore space, either in the waste or the well or in soil, that gets filled with gas and has an apparently high concentration, but very little volume. So, you get landfills that are functionally stable in every regard, but still have methane concentrations above 35%, 40%. What I'm really more interested in is what's the methane emission potential. So what's the concentration times the generation rate? Because that really tells you, that gives you a flux, and a flux is what tells you what an impact is. A concentration doesn't really tell you what an impact potential is. And the simplest example being you could have a very high concentration but almost no generation, and the flux associated with that would be very low. Conversely, you could have a relatively modest concentration but a high flow rate, and the flux associated with that would be pretty significant. So it's really concentration and generation are both important, but primarily generation, because generation tells you how actively gas waste is degrading.
Okay. All right, Jeremy, we have probably 15 to 20 more questions. So can you go to the last couple slides? We'll handle these in our podcast next week.
Sure.
Here's the contact information for Jeremy, myself, and Jennifer Miller. If you have additional questions on post-closure care of landfills, just please send them to one of us, and we will address them next week in Jeremy's podcast on May 26th. Okay, Jeremy, next. Our next webinar will be testing and design of geosynthetic drainage composites. This includes the textiles and the geonet that are bonded together to create a drainage geocomposite. That is Tuesday, June 16th, and the presenter is Eric Blond from Canada. Okay. Finally, I'd like to wrap up today with a list of the resources available on the FGI website, our online PDH program where you can go and watch any of the webinars that have been recorded previously if you missed them, and obtain a PDH certificate for the hour. Also, we have some new podcasts. These are video podcasts where we actually record video. The first one is a landfill case history, a slope stability case history, as well as demonstrating some of our geomembrane leakage and pond leakage calculators. Also on the website, specifications, guidelines, test methods through videos, and so on. So visit fabricatedgeomembrane.com. Jeremy, thanks again for an excellent webinar and joining us from Columbia, Maryland. I will talk with you on May 26th. Thanks.
Thank you.